part 2 of the free response portion, and then we'll get into the multiple choice portion. Yes. Yes. Lydia and Bob, I know it's really small up on the board. You guys have it written down in front of you,
Are they going to
so you can read the hard, difficult stuff. I will zoom in on this thing. As a matter of fact, I think it's just too small, so we'll increase the size of it here. Oh, Lydia, say happy met Lydia. Lydia, the tattoo lady.
Oh, you're not actually going?
That's a real song.
What about no one else?
It's a song about a woman that has like different countries of the world tattooed all over. On her tibia is Lydia.
And we'll literally find the I didn't like that laugh.
Like, I can stop my life, it's fine.
Wow, we gotta focus. Okay.
Yeah.
All right, we found data on the number of commercial aircraft flying in the United States during 1990 1998. States were recorded as year since 1990. Thus, the year 1990 was recorded as year 0. 1990 is year 0. The dates were recorded. It's a separate sheet of paper. Did you see the one we worked on yesterday? Yeah. There you go.
Yeah.
So they made a least squares regression line to fit the data. The graph of the residuals and part of the computer output for the regression are given below. So we got a residual output. Boom. We've got a computer output. Bam. Let's answer number 8. Is a line an appropriate model to use for these data? Data. Now that I know there's a difference between data and data, I have to change my ways. I thought they were the same thing sometimes.
What's the difference?
Apparently data is like collected observations, right? Data is like bytes.
I knew that. See, I'm not crazy. Since I
No.
just explained it like that,
Yeah.
because like I hate when people say like data. Like I'm out of data. I'm like you're out of data. Like, and I was like, there's a difference.
Yeah, I'm freaking out. It's hard. Okay, so, is it true that you could use a least squares regression line? Well, I would say based on the fact that there is no obvious pattern in my regression, in my residual plot, I would say yes, right? There is no
Josh, you need to wear a lovely sweater one of these
apparent pattern
someday.
in the residual plot. This suggests that a linear model is appropriate.
Yeah, when I bring you your Christmas present, you better put on.
Don't you love how in statistics we make these statements that you're like you can wiggle your way out of it if you wanted to? It suggests, Val, that, it suggests that it's appropriate. Copy. Nice.
So if it's wrong, they can't blame me.
Sorry. Okay.
Oh, and we get turned in.
What is the value of the slope?
This morning.
You're still late, but earlier than normal.
Of the least squares regression line, and let's interpret the slope in context of this situation. So let's go ahead and take that one step further, and let's go ahead and write the equation of the least squares regression. Okay? So the way that I remember what is what on this output is that your y-intercept is a constant, right? It's never going to change. So that means that, and it'll say constant. and then years. And it makes sense that right as your years increase, well, we'll talk about it. So this here is your y-intercept.
Understand my strange piece.
And if you still want to start with the problem, that's what's going on. We're going the number of aircraft, so years. So we're saying as the years increase, number of aircraft in the air should increase. And based on the fact that our slope is positive, that makes sense. So we could actually put, instead of x, we could put parentheses years if we wanted to, right? Plus our y-intercept. There it is. For this problem, I believe that's all we need. We're not going to have an r value or anything, but we got to talk about r values later. So that's okay. And all right. So what is the slope? The slope is 233. So this is our slope, 233.57. How do we interpret that in context? You would say that as the for each 1 year increase, yes. There are many equations, but you're probably, the chances of you having to use the other ones are, the chances of you having to create a least squares regression line from a computer output, 100%. Like, at some point in time on the AP exams, you will have to, which means that at some point someone's finding you. They'll try to make it pretty good. Alright, so how do we interpret it? We would say, for each 1 year increase, we expect, right? We cannot say you will lose points if you say the number of planes in the air will increase. You have to say we expect the number. It's a prediction, or we predict that the number of airplanes. We expect the number of planes, or is it flights? Number of commercial aircraft flying. Number of planes. Okay. Of planes to increase by. Okay. Okay, what is the value of the intercept of the least squares regression line? The value is this one, right? How do we interpret this? At year 0, we predict that there were 22,939.93. We do have year 0 in our data, our original data, right? Yep, we got data from 1990 to 1998. Perfect, then we are good. All right. So let's go ahead and just answer it. See. At year 0, 1990, we predicted number of planes. Is 2,939. All right. What is the predicted number of commercial aircraft flying in 1992? So are these year increments? 1 year increments? So in other words, x equals 2. So all we gotta do for D is substitute 2 in for our variable, and we will get some number. And it bothers me when people do that. Put this on. I don't know why it looks like it should go. Put it on like that. It's perfect. This square thing around here. 233.517 times 2 plus 2,939.93 is exactly 3,406. Whoa, 6.964 planes. Ooh, what was the actual number of commercial aircraft flying in 1992? How big was our residual? That's around 40, right? And remember, your residual is I should write equals actual minus 42. Sorry. Cool. Sorry, it took a minute for me to do that, right? And the way that I remember that is, if the point is above the line, you should wind up with a, no, I did it wrong. Yeah. I'm sorry. Actual minus predicted. Sorry. I apologize. The way that I remember that, and so I just when I was going over how I remember that, I realized I wrote it down wrong. Because if you have a value that is below your predicted, right, then you should have a negative residual. That's the way I remember that. So if it's below it, you should have a negative residual, which means that you would have a smaller number minus a bigger number, which should wind up being negative. That's just the way I remember that. So we'll go ahead and based on that, this value, y minus y hat, should be equal to 40, right? We know that this predicted value was 3,406.564. And then you can just solve it. You just have to add 40. I don't know why I had to make an algebraic equation out of it. You just have to add 40. That's just the way my brain works. If I could, like this makes me happy. This satisfies me in some weird way. Just adding 40 to it, I can't, I just don't believe it. I have doubt. And this eliminates my doubt. I don't know why. Fine. Alright. Okay, moving right along. Let's get back into multiple choice. But let's be a little more selective. There, I think, are 40 questions on this. But let's be selective about the questions. I'm looking for. So I'm gonna go through this. We've missed a bit of stuff from chapter 6 where we're looking at probability distributions. There was a bit of probability in the last one that we did. We're missing a bit of least squares regression, and then I think that was kind of it. So we'll go through and kind of nitpick stuff that looks a little more challenging. A little more. What shall we start with? I feel like my eye is drawn to this pie chart. There's a reason I want to do this problem. But it's not that good of a question, actually. So, oh, oh, we got an ogive. Yes, that's what we're missing. All right. Okay, Japanese cars get significantly lower gas mileage than cars from other countries. What is this showing? Wow, that's ridiculous. Okay, I'm starting to like this question a lot less. It's lower because it's at the bottom of the chart, guys. Okay. Yes, and it worked out really good. Thank you. All right. I don't know what any of this means.
That's me looking at everything.
Boom. It's E. That's the only thing we can know from this chart. Not really, not. Okay. Ooh, an overdrive, yes. Been a while since we've seen one of these. And relative cumulative frequency plot. Boom. Study wished to classify the students as light, moderate, heavy, and problem drinkers by the amount consumed per week. About what percentage of students are moderate drinkers? That is, consume between 4 and 8 ounces per week. Sweet tea. Because one beer is only 12 ounces. So by this measurement, I'm a heavy drinker. Oh, it's Gordon. Because I have one beer a week. It must be. It must be liquor. Okay, 48 ounces. Right about in the middle of there. Looks like around 40%. That is how you read, right?
I'm confused.
Oh, that's actually a question.
I just like
What video? Okay. Ooh, beautiful. Hey, oh my gosh. You guys have done this problem before. It's a pretty common thing. So the idea is when you convert it, right? When you convert your mean, you both multiply and add, right? But when you convert your standard deviation, you only multiply. So our new mean, our new one, is going to be don't know why the degree sign is 36.5 times 1.8 plus 32. Our new standard deviation. Our new standard deviation is going to be just oh, our new standard deviation is going to be 0.3 times. Just keep in mind, this constitutes as a linear transformation. If you're going to do a linear transformation on just a mean or standard deviation of a data set, or even the mean and standard deviation of some random variable, you will only multiply your standard deviation and you will do the addition and the multiplication portion of the transformation to your mean. So, for this problem, you're going to have to add all these up, figure out the percentile, then we should probably do it. Okay. Alright, so how many actual frequency of closing prices? So this is closing price. I love how you're required to label your graphs, but this one is not labeled. There's your frequency. So, how many total closing prices do we have? 13 plus 8 plus 15 plus 7 plus 2 plus 3 plus 1 plus 1. Okay, so there are 34. Alright. So 0 to 10 constitutes 13 divided by 34. I'm just trying to organize myself in the right way. I was gonna try to write them in here, but it's not gonna be nice. So I'm gonna actually have to make a table. I just need to make sure I have enough room for my table. So 0 to 10 is about 38%. And then we're going to have 11 to 20, which is 8 divided by 34, or 0.24. And then we're going to have 21 to 30. Right, just coming up with our frequencies, relative frequencies, and then we'll look at cumulative relative frequencies. Yeah, we are. Alright, that's 15 out of 34, or at 31 and 40 is 7 divided by 34.21. Yeah, I knew that I was worried about there being room. 41 and 50, 2 divided by 3, 4, 5. Dang it, this is gonna be weird. One. 3, 0, 3. And then from 71 to 80 is 0. And then we've got is 1. Let's see here. So which percentile are we at? Alright, so we have to establish a place for everything. So 0 to 10 is 13. So this is 1 to 13, and then up to here is 13 plus 8, or 21. And then we're going to add up 15 more on that, or 36. And then 31 to 47. Sorry. 61 to 70, I'm going to continue on. Sorry. Okay, so this, we're going from 21, so 31 to 40, I should have added 2.
36 plus 7.
36 plus 43, you're right. 43, and then we're going to do plus 2, 45, plus 3, 48. Plus 1, 49, still 49. Plus 1, 50. Cool. So now we will have we will divide this by our total that we have, right? Okay, cool. So now we are at 13 divided by 50, and then 21 divided by 50, 36 divided by 50. This gives us our relative standing. Okay. Which one is at 80%? That's where we need 45, somewhere around there probably. This is my calculator, so it's okay that I dropped it. So the range from, so I got 43, so 36 divided by 50 was 72, 43 divided by 50 was 80. So the range that contains the 80th percentile. So this one was 72. This one was 6. So the range that contains it. So it's the 30 to 40. Right?
They're like garbage lately. Like all of their articles, like it makes more like science.
Must be someone else, right?
That's what happens.
Not someone recording.
Like actually, exactly that. And then I'm like, what does this mean, Cosmo? What does it mean? And now they're targeting me again.
You guys understand 6? We've gone over that. We have not looked at a box plot. So, which of the following is not correct based on this box plot? About 50% of male students have weights between 150, not correct, between 150 and, so we're looking at males, 150 to 185? Is that at 185? I guess it maybe is at 185. So that's true. Remember, right, these box plots, right? Each one of our lines, right? Remember, we have min, quartile 1, median, quartile 3, max, right? In between each one of those arrows is 25% of the data. About 25% of female students have weights more than 130 pounds. Yeah? Sure. That's right. The median weight of male students is about 162. Sure, that looks about right. The mean weight of female students is about 120 pounds. What? Because of symmetry. Let's see. Oh. The male students have less variability than the female students. Oh, great. The mean weight of female students is about 100. I don't know which one. Huh? They seem both not correct. Huh?
He is, because he knows.
For D, yeah, it looks like, okay, it looks like, because the data is fairly symmetrical, then you would imagine that the mean and the median should be close together. Right? So I guess that will, that's, I think that this one is the one. I mean, because there is definitely way more variability in the male's age than the female, or weights.
It's like in like a dark room, but it's like they're really.
For 10. For the density curve, which statement is true? It is not symmetric.